Welcome to today's explainer made by Forge College. Today, we're diving into load balancing experiments. As part of our advanced Solana concepts track, specifically looking at optimization techniques for sea level, we are putting on our lab coats today. We're bringing some serious mad scientist energy to the table because we're going to design a highly controlled test harness, stress test our system, and figure out exactly how to optimize our workloads.
So remember our last lesson, the one on applied performance tuning? We played detective. We profiled the system and we spotted exactly where the pain was coming from. Those nasty queue buildups and those absolutely frustrating per-core CPU stalls inside our validator. We had certain transaction families just hogging all the resources while others literally sat there idle. So we found the bottlenecks, right? But how do we actually fix them? Well, that is our exact goal for today. We're taking those profiling insights and setting up a fully controlled experiment to test some concrete solutions.
Here's our quick protocol for the lab today. We'll start with a welcome to the lab, look at 3 balancing strategies, build our benchmark, run the experiment, and then, of course, analyze the results. All right, Section 1, welcome to the lab and our experimental design. Now, profiling tells us exactly where our sea-level execution is hurting, but to actually cure the patient, we need experiment-driven load balancing. This basically just means distributing incoming work across our execution resources to reduce those hotspots. Think of it kind of like a supermarket checkout line. If every single transaction queues up at register 1, well, that CPU core is going to start sweating, right? Meanwhile, the other cashiers are just standing around doing absolutely nothing. Load balancing is exactly how we distribute those shoppers across all available registers in our validator to keep that line moving smoothly. Moving right along to Section 2 are 3 balancing strategies. We're going to test 3 specific checkout line rules. And our first contestant, round-robin assignment. This is the absolute simplest rule of the bunch. It simply means assigning transactions cyclically across execution queues or worker threads. Basically, shopper 1 goes to register 1, shopper 2 to register 2, shopper 3 to 3, and then, boom, it loops right back to register 1. It strictly repeats the order. It's just blindly dealing out work regardless of how full anyone's shopping cart actually is.
Next up, we have hash-based partitioning. What's really fascinating here is how it routes transactions by a stable key to maximize cache locality. To stick with our grocery store analogy, it's kind of like sending everyone wearing an orange shirt to register 1 and everyone in a green shirt to register 2. By computing a stable integer from a transaction key, like, say, an account address modulo the number of queues, we keep similar tasks grouped together deterministically. This is brilliant. Why? Because it makes fetching data so much faster for the CPU, since related data is already warmed up in the cache.
Our third strategy is adaptive load-aware routing. This strategy actually monitors live metrics inside our Solana node and routes new transactions away from congested queues. Think of this as the smart floor manager standing at the front of the store. If they see someone at register 2 trying to pay for a giant flat screen TV using entirely pennies, they instantly redirect new shoppers to registers 1 and 3. It adjusts dynamically based on a depth threshold. And what if every single register is completely swamped? Well, it elegantly falls back to round robin, just to avoid starving anyone. Okay, Section 3, building the benchmark. To actually test these strategies, our script has to keep the workload mix completely constant. The only variable we swap out is the routing strategy itself. So step 1 of our clean architecture is the workload generator, which emits a highly controlled transaction stream. Step 2 is the routing logic, where we plug in one of our 3 strategies. And step 3 is the metrics collector. Separating the generator from the routing and the data collection is absolutely crucial here. It completely prevents any cross-contamination in our code and ensures we're truly isolating cause and effect. So the key point is that we must capture these execution optimization metrics into clean, time-stamped CSVs. We are tracking throughput, tail latency, queue depth, and CPU utilization. And here's a pro tip for you. We're highly prioritizing the 95th and 99th percentile tail latency, those P95 and P99 metrics, over just raw average throughput. Why do we do that? Well, because in performance tuning, it's those extreme edge cases, those slow outliers that really define a poor user experience. Moving into Section 4, running the experiment. Now, a massive word of warning here. Please do not run these tests on a live, noisy network. You absolutely must use a controlled local validator or a dedicated Solana testnet node to avoid chaotic traffic. Here are strict rules of engagement for these runs. First, we must use deterministic pseudo-random seeds.
Second, we have to maintain a perfectly constant transaction mix. Third, we execute 3 runs per strategy to ensure consistency. And finally, we log our decisions with minimal overhead. I really can't emphasize this enough. Without strict seed control and a fully reproducible environment, any performance differences you observe are probably just natural run-to-run noise, and that would literally ruin our beautiful experiment.
All right, the final step, Section 5, analyzing the results. Let's dive into what our pristine CSV data is actually telling us. For round robin, we should see a perfectly uniform per queue depth. For hash partitioning, the data should reveal a much lower variance in per queue CPU utilization, which confirms our cache locality is actually working like it's supposed to. Now, for the adaptive strategy, we want to see responsive latency shifts within 1 to 3 seconds of a queue spike. And across all of our runs, our main target is the throughput coefficient of variation of less than 10%. Hitting that proves our testing environment is completely stable. So let's summarize all of this. Deterministic workload generation, targeted tail latency metrics, and responsive load-aware routing truly form the bedrock foundation of execution optimization. By cleanly separating our workload generator from our routing logic, we successfully isolated cause and effect. And you know what? That makes these benchmark discoveries incredibly actionable for you as a developer optimizing C-level execution. You aren't just guessing anymore. You actually have the hard data. So, I've got to ask, are you ready to take these benchmark CSVs deep into the validator's internals to hunt down those pesky execution stalls? Because that is exactly what we're going to be doing next. These CSV artifacts and JSON summaries will be your primary tools in our next explainer on debugging contention and advanced execution paths. Thank you so much for joining me in the lab today. Be sure to visit forge.college to check out our data analysis courses, explore other Web3 related topics in this track, and just keep advancing your skills. I'll see you in the next one.